I'd like to thank everybody for being here today. Thin shell concrete, it's pretty amazing in my mind. I've been working with it for a little over 10 years now. You know, when I was back in school, I had a professor, Dr. Joe, that he kind of taught me a lot of things, both in the classroom and about life. He would always tell us to EL, to enjoy life. He would also tell us about, you know, he was a geotechnical engineer, and he'd worked for the Florida DOT for several years. And he'd always talk about the person who was doing the liquid limit, the Casa Grande test. If you guys all know that, you got a little wheel that you're turning and a little cup full of clay. You've drawn a line through it, and you're just counting every single time that goes around, and that cup drops and hits. He would say you could always tell who had to do that job because they were just a little bit on edge all the time because they were one, and then it would hit. I kind of think FEA analysis, I think we're kind of in that same boat there. We get kind of excited sometimes about pretty pictures like this, about different sorts of models. So with that being said, I'm going to talk a little bit. I'm going to cover a little bit some of the stuff that Chris had talked about earlier, and Mark, and Charles as well. And then I'm going to dive into a little bit about what we should know about FEA. So, and I've got a handful of good pictures in here, so just bear with me for 1 second. So this right here, this is the Pantheon. It's a very famous thin shell structure. Thin shell structures have been around for a while. As Chris had mentioned, they're lightweight surfaces, and they rely on curvature to really direct the forces through them, to develop those membrane stresses. And that's something really important to remember, even as you're putting together this really fancy FEA model, to be aware, like, what is going on. And it's something that the ancient civilizations, they were able to do. And so when we're doing an FEA model, we can think about that. And as Charles mentioned, thin shell structures, they minimize material, and so that's a pretty good thing. Characteristics and some benefits of the thin shell is the high strength to weight ratio, the material efficiency, the aesthetic appeal, and the structural efficiency. I think all of us, we see thin shell structures out there, whether it be concrete or whether it be a steel structure. When we see those, it always makes us stop and say, that's not a post and beam structure. That's something different. And that geometry that kind of makes them unique to kind of look at and to appreciate, that additionally helps with their strength. I've got a figure here that kind of goes back to kind of the Gothic cathedrals. You got a flying buttress right there, and that flying buttress, that shape, that helped give the cathedrals their strength. And in an FEA analysis, we're trying to take advantage of that as well. We're trying to understand the structure and make that work. One thing that I want to point out here, though, is I've got that they accurately capture complex geometry and load interactions, and there's a caveat associated with that. Accurately is all dependent upon the modeler and the model that's being made. One of my favorite quotes to think about is, all models are wrong, some are useful. And with FEA, they're all models, and they're all useful. Well, they're not all useful. Some of them are useful if we put them together correctly, if we've taken consideration of the different roles of the different materials and such. So real quick, I'm just going to go through some common thin shell geometries that we've kind of already talked about. So we've got domes, hypars, vaults, freeform structures. These are some common ones. I've got another list a little further down. Specifically, domes are typically spherical or nearly spherical, and they're historically significant, and they're really great at spanning large areas. Charles, he talked a little bit about that with water tanks and industrial storage. Hyperbolic paraboloids, they're the potato chip. We see these right here. I mean, that's why we all love Pringles, right? And when we're kids, we all understood like Pringles are really strong because you could flip them over and make the duck lips with them, right? So, like, we were introduced to shells at a young age, and the interesting thing about hyperbolic paraboloids is that they've got the reverse curvature to them, which gives them different analysis things that you have to kind of think about. We've got vaults, so from barrel vaults, where this would be just a single arch, to groined vaults, and back during the Renaissance, they came up with some of these things, and we look at these structures today. If you think about some of the older cathedrals, they have those groined vaults in there, and they're also very good at they're very efficient at spanning and carrying loads. Okay, grid shells. And I'm going to apologize right now to all of us because I recognize that's not concrete right there. So I'm sorry. But these lattice shells, there's a lot of the thin shell concrete analysis methods that you have to use. They apply to shells like this. We just did an analysis on a 50-year-old lamella dome in the southeast United States, and the same things that we did, we were able to use kind of our closed form solutions to kind of like to gut check some different things. But they're neat to see and to analyze as well. Another one is freeform structures, and you look at, I'll back up here, like a dome, pretty easy to analyze, especially when you think about an arch and then rotating it 180 degrees, as Charles mentioned, and then getting that extra benefit from that double curvature. Same thing with the hyperbolic paraboloid. It's got the double curvature. Vaults are single curvature, pretty easy to kind of think about. And then you get something like this and you're like, oh, like that's kind of a interesting structure right there. And at first glance, it looks pretty simple. It looks like a small barrel vault. But then you notice that the foundations don't necessarily line up with each other. There's this extra degree of curvature right there. So you think, well, how am I gonna gut check that? How am I gonna analyze it in the first place? And these are really good ones to apply a finite element model to. So some of the other ones, like I said, I mentioned in here, cylindrical shells, hyperboloids, grid shells, conoidal shells, elliptical and parabolic shells, funicular shells, barrel vaults, folded plates. Like Chris mentioned, there's quite a bit in ACI 334 that groups all of these shells, and there's some differences to think about when we analyze each of them. So just a real quick analysis or overview of closed form shells. So closed form shells, or closed form analysis, really goes back to kind of an undergraduate understanding of statics and mechanics. And it kind of starts off with some beams. That's where we kind of first get introduced to a closed form analysis. Those same brilliant engineers and scientists that came up with these methods of analyzing a beam, they did the same thing, and they started to, or for shells, they looked at plate and shell theory. They addressed mathematical equations for the geometry and the boundary conditions and the loading. And a lot of times they had to make some simplifications and idealizations. And that's not necessarily bad. Like I said before, all models are wrong, some are useful. They're models, even though they're approaching a perfect solution instead of a numerical solution, they're still making some of those simplifications. So within there, they were kind of able to take or identified different kind of loadings that and some closed form solutions for each of these: fluid pressure, temperature, uniform gravity loads, lateral loads due to wind and seismic or granular. And when they got to small openings and simple curvature, or differences in the curvature, then their methods kind of broke down a little bit. One benefit, though, is they can get fast results with their models. They're fairly easy for a computer to solve, and they're easy to solve by hand for a lot of these things. This is one of my favorite pictures right here, because it kind of it shows you kind of how to calculate your lateral stresses and your vertical stresses in a dome shell for a projected load on top. Is that projected? I think it's a uniform load on top of a dome. And so you can solve that pretty quickly by hand and get a feel for what the stresses should be. So those math, the differential equations, they're kind of a little scary there sometimes, but they usually break down into something kind of nice. And like we've talked about before, the membrane theory, bending theory, or shells operate through membrane stresses. And so we're able to kind of simplify a lot with that. So some of the advantages of using a closed form solution is the speed, the accessibility. You can start off learning these really quickly. And it can help us to kind of understand the fundamentals of what's going on. And I've noted that several times, and I think that's really important to know, is that we should understand the fundamentals before we even turn our FEA program on. Some of the limitations are we get into some areas like this right here, where we know we're going to have some sort of stresses or stress concentration due to the geometry changing right there. Boundary conditions are another area where we will have some issues. A lot of times we have to simplify our materials and our geometry for those closed form analysis. So kind of to compare this with the FEA method, we have the application, closed form analysis is really great for the preliminary design. But once we start getting into more complex topics, we need to start thinking we should probably use an FEA model. And, the FEA models have been around. This is Ray William Clough. He kind of helped pioneer the FEA model, or the FEA method, along with several other engineers. And that was kind of in the 40s and 50s they were starting to bring that out. So we're going to kind of move over into the finite element analysis now. And that's kind of taking this right here and taking that discretized element and putting it into the whole picture there. So, and I put my slide in the wrong spot. That's okay. We'll come back to it. So, finite element analysis, some of the things that it does really well that we're not picking up with the closed form are large point loads, geometric irregularities, nonlinear loading, material and structure interaction, construction phasing. Some of those things we can do, you could do a construction phase with a closed form solution, but it may take you quite a while to step through each step on there. Some drawbacks are FEA software is not cheap most of the time, and it's time consuming to learn it. I've tried to learn several others, and it's hard to figure out where's the button in here when my software does this, and I know it's got to do it. And so you have to be highly trained to use it, and to use it well, and to make sure that you can validate your results. So the fundamental concept of finite element is to approximate the shell into smaller discretized units or elements, and we're going to use that to approximate the structure's behavior. And FEA, it's based on those same principal fundamentals of mechanics that we use to define or to derive those closed form solutions, and that we've used to define beams or plate elements. So like I mentioned before, FEA is really great at handling complex geometries. It's versatile. We can handle different boundary conditions, different loads, and combine them in different ways. Another thing that's really important is we can capture some of those non-uniform loadings and any asymmetries that will come up. Right here, this is a dome that was built quite a while ago, and we had to go back. They had some questions on it, and we were able to go back and take a 3D scan of the dome and plug that 3D scan in and analyze it and see, hey, how has this changed as settlement has occurred or the actual as-built condition of the dome, and how does that change what we're able to do with it? And that's something that you really can't do with a closed form solution. You can't build an as-built model and check it like you could for a post and beam structure. So kind of the core steps in the FEA model is to pre-process the model. So that's figure out your geometry, model that geometry, and then after that you apply a mesh to that. You apply your loads to that mesh, and then you solve that model, and then you start interpreting the results in your post-processing stage. And your post-processing involves looking at not only the stresses and the strains, but the deflections. Another important thing is strain energy and buckling. So some of our challenges that we run into is that it's computationally costly to run these models. With the availability of computers today, and not just computers, but fairly fast computers, we can get that computational time. We can address that. You have to know really well that mesh and where you're going to have problems. Looking for a mapped mesh that will help kind of check different areas like this that are going to be a problem, and meshing it appropriately. And then understanding how we're going to simplify our FEA model. Our closed form analysis is already simplified, but sometimes we can't just model every single part of a shell. And so we have to figure out what can we do, how can we simplify this. The other thing we can do, we can use complex load cases. We do a lot of granular storage, and so we can apply those granular storage loads against the side of a shell. We can take into account material nonlinearities, looking at time dependent. It's right here. Maybe not. Well, we can take into account creep within the concrete, or cracking in the concrete in those tension zones, and the yielding of the reinforcing at those points. Again, there's some trade-off there. Are you going to go through and model that, or is that even worth it? That's something that you kind of have to learn. I think I really liked what Mark was talking about when he talked about the cathodic protection on the cooling towers, and how it was just more computationally beneficial to assume that 1 inch of concrete wasn't there, and check your stability with that. The other thing you can do with some programs is you can optimize your design, and you can have the program itself adjust those element thicknesses to account for or to find kind of the ideal design. Again, there's some computational power that or timing that you're losing with that. But it is an option, or you can manually and iteratively do that. So another thing we can kind of look at is if we've got large point loads on a hemisphere, on anything. For example, this is a 200-foot diameter dome with a 20-foot opening in the center of it, and we had to support 500,000 pounds on top of there. We were able to kind of look at this and say, okay, well now we can, if we stiffen that, not only are we adding a point load up here, but we're changing our geometry as well, and we could account for both of that, or both of those. We can account for large openings in the side of a shell. Chris talked about having a barrel vault with a stiff side and an unsupported flexible side. That's something that the FEA kind of helps with. You can kind of look at your seismic and wind loads, retrofits, and my slide. I apologize, my text ran off my slide. I didn't catch that. Let's talk a little bit about some, I don't know if I called them requirements, but some things to think about when we're talking about an FEA program. We need some way to support complex shell geometries. At the end of the day, we're just mapping a bunch of nodes on there. You can do that in Excel if need be to get that. If you can bring in, a lot of times you can bring in some sort of CAD file and map a mesh on there. Being able to map that mesh dynamically on there, change kind of in these areas around the circle here, or as you got two circles here, adjusting your mesh as needed, right? Those are good things to have within your FEA program. Kind of the concrete specific material models. Some programs have that nonlinear concrete behavior. They have reinforced concrete behavior. They can take into account cracking. They can take into account the time-dependent nature of materials. You can kind of look at what kind of different boundary conditions do I need? How complex do I need them to be? Do I need springs on certain areas? Do I need fixed, or just am I okay with pinned? And so you want to be able to take into account all of those, all sorts of loads that you can put on there, time-based or directional. And sometimes you want to do some long-term analysis, some dynamic analysis for seismic, or to see the effects of creep on the structure as you're looking at stability. You want to make sure that your solver is efficient at solving shell elements, and that it can handle any nonlinearities that you're going to take into account, whether that's a true nonlinear analysis or not. And these structures are big. I think, Mark, you said 400 feet tall. So that's a lot of elements in there, and that you want to be able to manage that many. So, and then as far as post-processing, you want a lot of opportunities there. High quality visuals are not just for publication, but they help you kind of see what's going on in the model. They will point out different stress areas. I've got a few slides further down that they talk a lot about. That we can see that what a good presentation kind of can do for you. So you want to think about like your user interface, your compatibility with other softwares, validation. You want to make sure that it's been validated some way so that you can trust the solver that's in there. So some popular ones are Abacus, ANSYS, SAP 2000, RFEM, FEMAP. Those are all good softwares, I guess. So I'll go through a quick case study right here. So I did a quick model of a dome. So, and we've got our boundary conditions down here. We're pinned at the bottom. We have an opening in here. We're just running a gravity load on there and a live load. And there's our live load right there. Like I said, your graphics, they're really helpful a lot of times to tell how is my load being applied here. You can kind of see we have a 30 PSF load that's projected onto the dome, and as it goes down to the side, it drops to 0. That's a good check we can make. So these are the deflections that we kind of see right here. So we got a bunch of load up at the top. It's a dome. We've got gravity working on it. Okay, that's something that we would expect to see. As far as hoop forces go, that's the kind of the stretching of the dome in the latitude direction. If you kind of think about it as a globe, you can see right here, we've got these heavy stresses right here that our closed form analysis wouldn't necessarily pick up. On the flip side, if we look out here at some distance away from that opening, we kind of get a constant band all the way around there. And so we can kind of see, oh, we're getting some issues with that. We should probably look at that. And our highest stresses in here, they're not right there. They're above this opening. Okay, maybe we want to look just at a certain section of elements right there. Similarly, the meridional forces, that shows it really well. We're not getting a lot of granularity in our contour because we have such high stresses right here. Okay, again, maybe we want to look at something away from that opening. So, and then lastly, we can kind of check, okay, we've got our closed form solution right here, looking on the back side of the dome. We can look at this and kind of compare, oh, we've got the same values right here. We're seeing reversals in our load from positive to negative. Same thing right here. Right here, here's the bending. So I think my time is up. Does anybody have any questions?